Hello, chemistry students. Today is a big day. Today we get to talk about Avogadro's number. And by the end of this lesson, you should be able to understand and use the unit of a mole. Now you might be wondering, what is a mole? Well, I'll answer your question with a question. What is a dozen? What is a pair? And what is a baker's dozen? You know the answer to all three of my questions because you know that a dozen, a pair, and a baker's dozen are all vocabulary words that represent a counted number. So what is a mole? It is a counted number of representative particles. It would be really hard for scientists to figure out the properties of one atom, one molecule, or one formula unit of a substance. So what they do is they have a counted number, a mole of atoms, and they compare the properties of one mole instead of one particle. So, like I said, a mole of a substance is exactly 6.02 times 10 to the power of 23 representative particles of a substance. Now, 6.02 times 10 to the 23 is a very important number to have in your notes. We're going to use that a lot, and you are going to use it in calculations today. Okay, so the types of representative particles we work with in this class are atoms, molecules, and formula units. And from here on out, you need to be careful about the 7 elements that normally exist as diatomic molecules. So if you see them by themselves in a chemical formula, make sure that you add a little 2 as a subscript next to it. And in order to remember what these 7 elements are, you just have to remember the word Honkelbrief. So if you see H, here's an example. You could see this formula. When you see this, you just have to remember that hydrogen and oxygen typically exist as diatomic molecules. So if they're by themselves in a chemical formula, you have to add a little 2 because that's how they exist in nature. Nitrogen, chlorine, bromine, iodine, and fluorine all do the same. So important things to have in your notes from this slide are 6.02 times 10 to the 23 equals 1 mole, and a list of atoms that typically exist as diatomic molecules. Okay, so now that you have an idea of what a mole is, let's talk about how we can use a mole. The mole is like the gateway to conversion problems in chemistry. And once you understand how to convert using the unit of a mole, you can do so much more. And second semester will be a lot of work with the mole. Okay, so all of the roads go through mole. If I were to ask you how many representative particles are in 2 grams of chlorine, you would have to convert by starting with what you know, mass. You'd have to go through mole and then all the way down to representative particles. There is no calculation that goes straight from mass to representative particles. It just doesn't work. So let's start with conversions involving fundamental particles. Okay. When you're going from fundamental particles into moles, what you use is Avogadro's number. And the unit for this is, we'll call it atoms, could also be molecules, per mole. The symbol for mole is MOL, all lowercase. Just leave the E off so you'll see it that way sometimes. So if you're converting from moles to fundamental particles, you will multiply the number by 6.02 times 10 to the 23. And if you're converting from representative particles to moles, you will divide your number by 6.02 times 10 to the 23. When you're doing conversions involving mass, you will use the periodic table because the mass depends on the molar mass of the substance you're using. So specifically from the periodic table, you will use molar mass. And the unit for molar mass is grams per mole. And finally, we'll talk about volume. We'll come back and cover STP in more detail later, but you can know right now that STP means standard temperature and pressure. So these calculations only work if the gas is at standard temperature and pressure. Okay, if the temperature is high or low, or the pressure is high or low, this calculation is not the same. But I will tell you that 1 mole of gas at standard temperature and pressure takes up 22.4 liters. And like I said, we won't be doing calculations with this number today, but while you're copying this diagram into your notes, that's a good number to have on your diagram. We'll come back to it. Okay, and I just wanted to review with you where the atomic mass can be found. It's right here on the bottom of this periodic table. If you're looking at a different periodic table, you just need to look at the key and figure out where the atomic mass is. We've worked with this a little bit in the past. And also, if you're working with a molecule, you need to add the atomic masses of every atom in your molecule together to find the atomic mass or the molecular mass of that molecule. Okay, here's our first practice problem. How many representative particles and how many atoms are in 1.14 moles of sulfur trioxide? Okay, so what do we know? We know that there are 1.14 moles of sulfur trioxide, and we want to find out how many representative particles and how many atoms there are. So this is where the math that we worked on at the beginning of the semester will come back. I'm going to start with my conversion chart and write what I know in the top left. Okay, so I'm converting from moles into representative particles. So I am going to multiply by 6.02 times 10 to the 23. There are 6.02 times 10 to the 23 molecules in 1 mole. And I can actually stop my calculation right here for now and figure out how many representative particles they are by multiplying. And I started out with 3 significant figures, so I need to count 1, 2, 3. What does 2 do to 6? Nothing at all. So my final answer is 6.86 times 10 to the 23rd molecules. So that's the first part of the answer. Now the next one asks how many atoms. And SO3 has 4 atoms per molecule, so I just need to multiply 6.86 by 4. I need to correct this and put it in proper scientific notation, and then correct for the right number of significant digits. So I'm almost done. I need to move my decimal place behind the first significant digit, which will change 23 into 24. And then I can only have 3 significant figures. So 1, 2, 3. What does 5 do to 4? It actually increases it. So my final answer is 2.75 times 10 to the 24th atoms. So there you go. That's our first calculation using Avogadro's number. Next, find the molar mass of PCl3. You're going to have to do this a lot going forward, so I thought we would just break it down with a simpler one. Okay, so I like to just list out the atoms in the molecule. So we have phosphorus and chlorine. And then I'll go to the periodic table and find their molar masses. So I'm going to take 3 significant digits off of this. So this is going to be 31, and this one's going to be 35.5. 31 grams per mole, sorry, 31.0, and 35.5 grams per mole. There are 3 chlorines, so I'm going to have to multiply this one by 3, which equals 106.5 grams per mole. I'm going to add 31 to that. So the final answer is 137.5 grams per mole. And that is the correct number of significant digits, so I can just box my final answer. Okay, next question. Find the number of moles in 3.7 times 10 to the negative 1 grams of boron. So what I know is that there are 3.7 times 10 to the negative 1 grams of boron, and I need to figure out how many moles there are. So let me set up my conversion chart. And I'm going to convert this number out of scientific notation. So there are actually 0.370 grams of boron. And then in order to figure out how many grams are in 1 mole of boron, I need to go look up the molar mass on the periodic table. There are 10.8 grams in 1 mole of boron. So since I have grams on the top, I'm going to want to put the same unit right here so that they cancel out. So 10.8 grams in 1 mole. Okay, then 0.37 divided by 10.8 equals 0.034259. And the unit that remains is mole. Moles of boron, actually. And now I just need to edit for significant figures. So there should be 3, 1, 2, 3, 5. We'll bump 2 up. So my final answer in scientific notation, I guess, is 3.43 times 10 to the negative 2 moles of boron. Okay, find the number of moles in 26.7 grams of hydrogen peroxide. So I know that there are 26.7 grams of hydrogen peroxide, and I need to find the number of moles. And I know that grams will be on the bottom, and moles will be on the top so that they cancel out. And I need to find the molecular mass of hydrogen peroxide. Hydrogen has a mass of 1.01 grams per mole, and oxygen has a mass of 16.0 grams per mole. So when we add these together, we end up with 34.02 grams per mole. And we need to edit that down to the tenths place, so 34.0 is what we'll put in our conversion. There are 34 grams for every 1 mole of hydrogen peroxide. So we just divide 26.7 by 34. One more edit. 1, 2, 3. 2 does nothing to 5. So our final answer is 0.785.